How's that? All right, much better. So let's talk about indefinite integrals. 4.1, indefinite integrals. Indefinite integrals, aka antiderivatives. Antiderivatives. Indefinite integrals or antiderivatives. Again, just as a reminder, a derivative, recall what I mentioned before, a derivative is both a slope of the tangent line as a value, right? If it's a value, like a number, you have the slope of the tangent line. If a derivative is an equation, it is an equation that describes how the slope changes. If a derivative is a number, like a value, like 7 or -2, it's describing the slope of a tangent line at a particular value, right? If your derivative is an equation, like we have the derivative of x squared is 2x, that describes how the slope of that original function is changing, how the slope of that function is growing or shrinking, right? If your slope is positive or your slope is negative. If your slope is increasing, your slope is decreasing, right? We have the second derivative that describes the curvature of the slope. So the first derivative describes how the slope is changing, if it's positive or negative. The second derivative describes the increasing or decreasing amount of change, right? The curvature. So our derivative is describing how slope changes. An integral, similarly, integral, has two kinds of ways to describe it. If it's a value, it means the area under a curve, or the accumulated change, accumulated in a curve, accumulated change, right? Like a distance that you've gone, for example, if you integrate the speed, you'll get the distance, right? The integral of velocity, for example, is equal to the distance that you've gone. If you take the area under a curve of velocity, right, your speed, you'll get a value of a distance, right? The accumulated change, how far you went when you were going these speeds. Right? An integral of velocity gives you a distance. But integrals can also give us equations. And if you get an equation, it's an equation that describes how the area changes in the function. It describes how the area is changing. Is the area increasing as you advance along the graph? If you go further on the graph, is the area going to get bigger? Or is the area going to get smaller, or is the area going to get negative? Are you growing as you increase, or are you shrinking as you increase the graph, right? What is happening to the area? This equation describes how the area is changing as the function changes. And so we can create equations of integrals. We can describe equations of integrals. An integral can also give us an equation. And again, that equation describes how the area is changing. As the equation, as we get further along the x value of the equation, is the area under the curve getting bigger, or is the area getting smaller? Or is the area getting negative? Are we losing area? Are we gaining area? Right? How is the area under the curve changing as we go along the x-axis, as we tool along under time or whatever value is. So to think about this equation, we got to think about an antiderivative. So we talked a little bit about this last class. I'll give you a preview. But let me remind you here. If you have an equation, a derivative, f of x, was equal to, I said, like 2x, what was the original equation? If this is your derivative, what was the original OG equation that gave us that derivative? And we said that, well, this equation would have to be x squared, right? You're going backwards, you think, okay, well, if I have a number in front, right, if I have an x, if my derivative is this x, my original function had to have x squared, because if I do a derivative, I know I decrease the exponent by 1, right? I bring the number down in front, and I decrease the exponent by 1. So this brings the 2 down here and makes that there, right? And we did this a few times, right? For example, if I have a derivative of something like x to the second power, well, I know that that had to be an x cubed, but I don't have, right, I have no 3 in front here, so where did the 3 go? And we learned that, well, if I imagine bringing down the 3 to kind of cancel it out, I have to make this a 1/3. Or I can just say, x cubed divided by 3. Right? We need the 3 to fill in, to kind of counteract, to cancel out the 3 that we bring down in front. Need to cancel out the 3 we bring down. Right? We need that 3 to cancel out the 3 that we bring down so that we have our equation. And so I want to go through how do we know, right? So basically what we're doing is we're doing the integral of these equations. If we do the integral of 2x, we're going to get x squared. Do the integral of x squared, we're going to get x cubed over 3. These integrals here give us these equations, right? But there's a little bit that's missing here. There's something else that's there's something else that's missing. But, whoopsies. But something is missing. Something is missing. So let me give you an example. When I do a derivative, let's say, for example, if I have f of x equals, x squared, I know that the derivative is 2x, right? But what if I have fx is x squared plus 1? X squared plus 1. What's the derivative of that one? Well, that's also 2x, right? Because this 1, if I do a derivative, the 1 kind of disappears, right? Or our constants go away. Or if I have x squared plus 2, the derivative of that is also 2x. And I can have anything. I can have any number here, right? So when we do a derivative, right? When we do a derivative, the number disappears. When we do a derivative, the constant disappears. So this is a problem for us if we want to try to go backwards. Because if I say, okay, well, my derivative of the equation was 2x. if I say my derivative is 2x, which original equation did I start with? Which one? Was it this one, or this one, or this one, or some other some other constant? Or maybe I did a subtraction. Maybe it was minus 100. Maybe it was plus 1,000. There is simply no way to know which original equation I started with if my derivative is 2x. It could be any number. There could have been any number, any value here that just got wiped away. And so when I do this integral, I have to imagine that there might have been a number that I just don't know, right? There might have been a number that I just don't know. So to fix this, we say the integral of 2x dx. What we say is, well, it's x squared. I know it's x squared, but I have to imagine there's maybe some constant at the end of the equation that's going to be there that's like hidden that I don't know about. I have to like account for this possibility. To do this, we add a constant. So this plus c, this is the potential, the unknown constant that we add to every integration. And every single integral, every single indefinite integral is going to have this potential constant that we add. Every integral we do, we have to say, well, if we're undoing a derivative, right? If we're undoing a derivative, that's why it's an antiderivative. If we're undoing the derivative, every single one could have had this constant here. We don't know. We add this constant on the end of our indefinite integrals. We say, well, in the original equation, there could have been a constant here that disappeared when we did our derivative, right? So we have to add this c. So the integral rule, the definition, or what am I going to call it? The formula, I guess you could say. So the integral, oopsies, the definition, I should say, the definition is the integral of f of x dx is equal to, we say this is a capital F of x plus c. Capital F, right? This is the antiderivative. F of x equals the antiderivative. Derivative. F we call the integrand, right? What is it? Antiderivative of f of x, lowercase f of x. So capital F, we use as capital F, or sometimes you can say the integral of f prime of x dx equals regular f plus c. But either way, you're adding this c here to the end of your integral, right? Every integral has this, every indefinite integral, indefinite integral. The definition of an indefinite integral works like this, where you have an integral. You don't have the bounds. Notice that there's no a and b. This is the general equation for an indefinite integral, when we're getting an equation out of our function, right? we don't have a boundary. We're not looking for a particular number or a particular area. We're looking for the equation that describes the area. The integral of f of x dx gives us the antiderivative plus this c. Every time we have to add the c. Because there could have been, right, if we do the derivative, this derivative, if we did a derivative, this constant got blown out. So when we do the antiderivative, the integral, we add it back as say, well, maybe there was a c here, I don't know, we'll figure it out later. Basically what we're doing. Well, there may be a c here, I don't know, we'll figure it out later. So this is how we do antiderivatives, right? When we're getting equations, right? When we do an integral of a value, we say, well, right, 2x, the derivative, if this is the derivative, the original equation was x squared, and maybe it had a c. So let's go through some rules, or some, like, not rules exactly, but I guess you can call them rules. Some examples of basic derivative rules. Call these basic integrals, I should say. Basic integrals. Basic integrals. Okay? Some basic integrals using the rule here. So the first thing is, if I do the integral of 0 dx, if I do the integral of 0, that's going to be a c, just a c, right? Some constant, right? If I have an integral of 0, for example, like if I look at, for example, a graph of y equals 3, right? Y equals 3. If I did the derivative of this, y prime equals 0, right? The derivative of this graph is 0, because it's just a straight line. But it doesn't matter what the number is. If it was a 3, it'd be 0. If it was a negative 10, it would still be 0. The derivative would still be, it's a flat line. So the derivative, the integral, I should say, the integral of 0 is going to be some number, a constant number. Some value, constant value. Okay? What about the integral of dx by itself? Integral of dx by itself. What if there's no number here? Well, if there's no number, remember this is like an invisible little 1. We have an invisible little 1 here, right? Invisible 1. So what's the integral of 1 dx? Well, what equation gives us the derivative of 1? It's just x. But we have to say there could have been a number. It could be x plus 2. It could be x minus 10. We don't know. The integral of dx by itself, you bring back the x into the equation. When you do an integral of dx, you bring the x back in the equation. And this is true of any integral with a number in front of dx. It's going to be k x plus c. If I do the integral of some number 7, some number -5, whatever the number is, right? I bring the number out, just like we did before, right? We bring our value out of the integral, and then do the integral of the dx, and that becomes an x, and the k just sort of sticks around. Constant sticks around. It becomes a coefficient. This k becomes a coefficient. And so this one, for example, if I had an equation like this, right? This is, for example, y equals 2x. The derivative of that is 2. But it also could have been y equals 2x plus 5. Or it also could have been y equals 2x minus 7. All of those have a derivative of 2. Because remember, this 2, this is the slope. R2 is here, R2 is here, R2 is here. It's the slope of the line, the rise over run. So if you go backwards, right, if we're going backwards from the derivative, our derivative is some value, some constant number, the equation had to be that slope times x, 2x. But it had to be plus c because, again, there could have been a number, I don't really know. Oops. All of these have this plus c in the end. Okay, well that's fine for dx. What if I have an x, right? What if I say it's x dx? What if I have an x there, right? Well, this is going to be x squared over 2 plus c. Right? Remember we talked about, well, if it's an x, I need to bring one more. I need to bring an x back in. If I'm doing an integral, I'm adding an x. I'm bringing an x back in. If there's no x, I bring the x back in. If there's an x here, I bring another x in, make it x squared. But to counteract the fact that I have this 2, right? Remember, I bring it down. To counteract the exponent, I then divide by the exponent. So I bring the x back in, add an exponent, and divide by whatever the exponent becomes, to counteract the fact that it's there. And so the general rule for this is if I have anything to the power of n of dx, it's going to be x to the n plus 1 over n plus 1 plus c. And this is my power rule for integration. Power rule for integrals. So this is the general rule that we have for all of these. Really here there's in this one here there's like x to the power of 0, so I add 1, I get a 1. Here there's an x to the power of 1, I add 1, I get 2, right? So it's really the same rule for all of these, but this is the general rule. Whatever the exponent of the x is, I add 1 to it, I divide by that, and then I add the c. Because again, there could have been any number of equations that all have the same derivative. Have to put the c there because like, oh, maybe there was a c, I don't know, we'll deal with it later. So let me give you some examples of this power rule that we use. So, for example, if I have the integral of 3x to the 4th power dx, solve this. Solve this. What is the integral of 3x to the 4th power dx? Well, I'm going to use my rule here. Really, I should say if there's a k in front, but it's fine. I'm going to do my exponent rule, right, where I'm going to add 1 to the exponent and divide by that, and then I have this 3 that just kind of sticks around, right? The 3 in front just kind of sticks around, right? We bring that coefficient out of the derivative, out of the integral. That k gets out of the integral, and it just kind of sticks around. So this is going to become x to the 5th power over 5 times 3 plus c. 3x to the 5th over 5 plus c. Or you can say 3/5 x to the 5th plus c, whatever you want. But there's your answer. That's your equation. Right? Power rule for derivatives, for integrals. Power rule for integrals. We're going the other way, right? We're undoing a derivative. We're adding 1 to the exponent, add 1 to the exponent, and we've got to make up the difference by dividing by whatever the constant was, whatever the exponent is. So add 1 to the exponent, then divide by the number. And this works for any kind of exponent, just like we had for derivatives. What if I have, for example, 1 over x to the 3rd power dx? It works for any kind of exponent. Well, okay, 1 over x to the 3rd power. It's a fraction. Does that make it harder? Well, not really. This fraction, remember what happens when I have an exponent on the denominator? I can just make that into an x to the negative third power dx. And now I follow the same rule. I'm going to add 1 to this exponent. So if I add 1 here, plus 1 is going to be negative 2. So I'm going to get x to the negative second power divided by negative 2 plus c, which is going to make, really, it's 1 over negative 2x squared plus c. And if I do the derivative of this, if I do this derivative, I'm going to get 1 over x cubed. Imagine doing this derivative, right? You take the negative 2, bring it down. Negative 2 cancels this negative 2. Negative 2 becomes a negative 3. You get 1 over x cubed. So this would be your answers here. Works for negative exponents too. Works for negative exponents. So if it works for negative exponents, works for positive exponents, what other kind of exponents does it work for everybody? Oh goodness. Whoa, goodness. Stop it. Stop it. What other kind of exponents? Fractions too. Fraction exponents. That's right. The integral of square root of x, everyone. What about this one? Ooh. You think you're worried? It's just the integral of x to the 1/2 power. Well, okay, if it's an exponent, I know what to do. I'm going to add 1 to it and then divide by that fraction. X to the 1/2 power. 1/2 plus 1. 1/2 plus 1. That's going to become 3/2, right? So I'm going to get x to the 3/2 over 3/2 plus c. Works for fractions too. Works for negative exponents, works for fractional exponents. Of course, this, I don't really like the dividing by 3/2, right? So again, when I have a fraction on the bottom, I do a little flip-a-do, right? So I get 2x to the 3/2 over 3 plus c. So that would be my answer for this one. I don't like fractions on the denominator, right? So I do a little flip-a-do, put the 2 up on top, leave the 3 on the bottom. Becomes my exponent there. Is it making sense? Is it seeing the pattern here, right? You're adding 1 to the exponent. Whatever the exponent is, you add 1, divide by that exponent to kind of make up the difference. So this is how we do integrals. We do integrals using this power rule, and they can get kind of complicated. What about this equation here? What about if I have, let's do 2x cubed minus 5x squared plus 7 dx. X cubed minus 5x squared plus 7 dx. If I had this equation here, I want to do the integral of this equation here. This is going to be some complicated cubic curve, right? We got some kind of cubic curve here. And this is my derivative. What's the original equation look like? What's the f equation look like? This is some cubic curved equation. What's my original equation look like? Well, if I do the derivative, if I do the integral, I'm going to do the integral of each piece separate. We talked about this rule with definite integrals. If you do an integral, you distribute it to all pieces. You do each piece with its own little exponents, its own little rule. So if I do the first one, 2x cubed, that's going to be, okay, add 1 to the 3. 3 is going to be 4, so it's going to be 2x to the 4th power over 4. And then plus c. But I only really need one c at the very end. So I'm going to hold off. Once I do all the integrals, I'm going to add the c in the very end. So there's my first one. Minus 5x, this is going to be to the power of 3 over 3. Plus, what's this last one going to be, everybody? What's the integral of 7? What am I going to put here? What would the integral of 7 be? These ones I had the exponent, right? I could add the exponent, then divide, add the exponent, then divide. If I just have a number, what's the integral with the antiderivative? What equation would give me a derivative of just a 7? What equation, what would the integral of 7 be? Look at your notes, look back at what we did when we just had a number. What would it be? Integral of 7. Who can I call in to make a guess? Adrian Anguiano. You were in here last. You get to go first. What would the integral of 7 be? Adrian? What do you think? Integral of 7. You there, Adrian? Earth to Adrian. Has he stepped away? Three more seconds, Adrian. All right, 1,000 points for Adrian. Oh no. Brain. All right, integral of 7. Give me a chance. Give you a chance. What are we doing when we do an integral? What we do is we're bringing back a variable. So if we do the integral of 7, let's look back. Let's look back. It's just like this one here. If I do an integral of a number, what happens? Well, I have that same number. I'm going to add on an x. Right? The integral of a number is just that number plus an x. So what's the integral of 7 going to be? What's this integral here going to be? Integral of 7 is what? Anyone want to help Adrian out? What's the integral of 7 going to be? Thank you, Party. So yes, 7x. Exactly. Thank you, Haley. Exactly. Thank you, Ayala. Perfect. 7x. We're just putting the x back in, right? When we did the derivative, we took an x away. Right? When we do a derivative, we lose an x. When we're doing an integral, we gain an x back. There's no x here to start with, so we bring it back and we make it 7x. Just like here, if it was cubed, I bring an x back when I do an integral and make it x to the 4th power. I increase by x's. Here, there was no x's to increase, so I give it 1. There was no x's to increase, so I give it 1. And then at the end, we do plus c. That's going to be our equation for this integral. It's going to be some kind of quadratic 4th power equation, which makes sense, right? Because when we do a derivative, we go from a 4th power to a 3rd power. When we do an integral, we go from a 3rd power to a 4th power. We increase the exponents. Interesting. Very interesting. Using our integral rules using our power rules to figure out multiple pieces doing integrals of each part. And if it's just a number, when you do the integral of a number, you give it an x, you bring an x back in. And then we have the plus c in the end, because we didn't know, maybe there was a number here. So if you think about doing the this 2 over 4, I should simplify this, shouldn't? This should really be 1 over 2. 1 over 2. All right, so we can do integrals of fractions, of negative exponents, of multiple pieces together. Let's do one more. So the integral of, let's say something like, oh, what's a good one? Give me a pretty good example here. Oh, yes, I like this one. X plus 1 over the square root of x dx. Ooh. X plus 1 over the square root of x dx. How do we do this one? So in this, well, if we were doing a derivative, we would have to do like low d high minus high d low over low squared, right? And there is no integral rule of a similar nature to that. Just like there's no product rule, really, for integrals. So what we're going to do instead, what we can do here is, you notice that there's one number on the bottom, and instead of making one big fraction, what if I separate it and make this into 2 fractions, like I have multiple pieces here? That's going to make our lives much easier. We're going to do the integral of x over square root of x plus 1 over square root of x dx. Separate the fraction. We separate this fraction, and now we can do a little simplifying with our exponents. X over square root of x. This is the same thing as x to the first power over x to the 1/2 power. Right? X to the first power over x to the 1/2 power. Well, if I do my simplifying, right, if I cancel out my x's, if I have a a over b, if it's x to the a over x to the b, that equals x to the a minus b. I subtract my exponents, right? When I divide, I'm subtracting. 1 minus 1/2, this is going to equal x and 1/2 power. So this is the integral of square root of x, or really I'm just going to say x to the 1/2 power, x to the 1/2 plus x to the negative 1/2 dx. And this now I can do. This now I can do. Right? I made my square root a negative square root. I made the 2 x's with different exponents, right? I subtract them when I do a fraction. I subtract my exponents, right? 1 minus 1/2 is 1/2. So this becomes x to the 1/2. And now I can do my integral. This is going to be, let's see, x to the 1/2 plus 1 from that. This is going to be 3/2 plus 1 is 3/2. And plus 1 here is equal to a positive half. Negative half plus 1 is positive half. So this is going to be x to the 3/2 over 3/2 plus x to the 1/2 over 1/2 plus c. Separate the fraction, and then simplify your exponents. when you have two exponents dividing, you subtract them. So 1 minus a half is a half. Right here becomes a negative exponent on top. So I get my equation here. And again, I want to do a little, a little flip-a-do solving, simplifying here. Flip-a-do that, flip-a-do that. So this becomes 2x to the 3/2 over 3 plus 2x plus c. 2x to the 1/2, I should say. There's your answer. We okay, everybody? Not too scary? Maybe a little scary. So that's with the power rule. That's one of our big rules of exponents we can use to solve these. Should I give you a couple to try? I do want to go through a couple more rules. I guess we have 20 minutes. Well, more like 10 minutes. All right. You'll be fine. This is the major rule, is the power rule, right? Especially with these fraction exponents and negative exponents. Just get yourself an exponent, and then it's much easier, right? You add 1 to the exponents, right? Once you get yourself an exponent, once you make your variable have one exponent, it becomes much easier. You just add 1 to it. All right, let me do some more over here. I got a couple more rules here. Oh, stop it. Stop it. Over here. A couple more rules to go through. Other basic integrals. So, for example, the integral of, let's do, maybe I should say these are well, other basic integrals, this is fine. Integral of the cosine of x dx. Let's do some trig ones. Trig. All right, we did some trig derivatives. Now we can do some trigonometric integrals. So, what's the integral of cosine of dx, everyone? Well, what equation has a derivative of cosine? Which trig function? The derivative of this trig function is the cosine. Derivative of something is cosine. Which one? Which trig function has its derivative of cosine? Derivative of this one is cosine. In the chat, tell me which one. Which trig function's derivative is cosine? Anybody remember? Yes, Stephanie. Say it to everybody. But I'm going to lose the E. Very good. The sine, right? Exactly, the sine. So this is going to be the sine of x plus c. So the derivative of sine is cosine, right? So when we go backwards, the integral of cosine becomes sine, right? You're doing an antiderivative. Same thing with the integral of sine, everybody. The sine of x. What equation gives me a derivative of sine? It's going to be cosine, right? Yeah, cosine of x. But very good, right? So it's going to have to be negative cosine, because when I do a derivative of cosine, it becomes negative sine. Well, if I go integral of sine, I have to have a negative here to right cancel out. Negative becomes positive. Derivative of cosine is negative sine. Negative makes this positive sine. So integral of sine is negative cosine. What about, this is a good one. What about the integral of, let's see, secant squared of x? dx. Ooh. There was a trig function whose derivative was secant squared. Anybody remember which one that is? Derivative of this trig function. Look at your trig functions, everybody. What trig function's derivative was secant squared? Thank you, Perry. So yes, that is tangent. The derivative of tangent was secant squared. And similarly, if we have the derivative of secant x tangent x, we're going to get that's a secant of x, right? Because the derivative of secant was secant tangent, dx. So we have all these backwards trig functions as well, right? You see sectan, it's going to be a secant, right? You see the integral of secant squared, it's going to be a tangent. We have a lot more. Let me do another one here. Let's go cosecant squared of x dx. That's going to be the cotangent. And in fact, it's going to have to be the negative cotangent of x plus c. And the integral of cosecant of x cotangent of x is the negative cosecant of x plus c. So a little bit of patterns, right? If you see secant squared, your integral of secant squared is tangent because the derivative of tangent is secant squared. Derivative of secant is secant tangent. Derivative of cotangent is cosecant squared, but again, the negatives, got to keep track of the negatives. All of the cos, by the way, cosine, cotangent, cosecant, those are all the ones you got to be aware of your negatives. Cosecant squared is cotangent. Just like secant squared is tangent, cosecant squared is cotangent, right? You're going to connect these in your mind. Connect these in your mind. Okay? Some more trig rules for integration. And of course, there's a lot more than just these. We have, just like we have a bajillion different ones for derivatives, we have a lot of different ones for integrals. So I will be posting a handout in our Schoology page with a lot of these, with all these on them. That again, you can print up, plus a lot more. And we'll be updating that list as we go. But this is how we do integrals, everyone. Antiderivatives. Finding an equation, right? Finding an equation, you do the, where'd my rule go here? Right, the integral is our definition here. Our integral of f of x dx is the antiderivative plus c. Integral of your equation is the antiderivative plus c. And so we have our basic integrals, right? If you have just a number, an integral of just dx by itself, it becomes an x, right? You bring the x back in. If you have a number in front, it's just that same number plus the x brought back in. You bring the number back in. If you have an x by itself, right, you increase the exponent by 1 and divide by the n. General formula for the power rule. And we can do that with negative exponents, with fraction exponents, with multiple pieces. We can separate our fractions into multiple pieces here and do the integral that way. Getting one piece by itself with your integrals makes it much, much easier. And then if we have some integrals with trigonometric equations, using all these trig integrals, right? You see the integral of cosine, integral of all these. Let me give you one more example here. One more example. What if I have something like this? Let's do the integral of 2 cube root of x minus 5 cosine of x plus 6 dx. Let's do the integral of this one here. Complex looking equation, but as long as we follow the rules, everything should be fine. 2 cube root of x minus 5 cosine of x plus 6 dx. First thing, I want to rearrange my radical here into a fraction exponent. What does the cube root become? Well, this becomes the integral of 2. Let me do it this way. This becomes 2x to the 1/3 power, right? Remember, when we have a radical, the radicand, number on the outside, becomes the bottom of the fraction, right? Because the square root of x, it really has an invisible 2 by default. Square roots always have invisible 2's, right? That's why it's a square root, because there's 2 there. So square roots have invisible 2's. So the cube root of x is x to the 1/3 power. So if I do this integral, I'm just going to do piece by piece by piece. This one here, I'm going to add 1 to the 1/3, which becomes 4/3. So this becomes 2x to the 4/3 power over 4/3. I'll deal with the fraction later. I'll deal with that fraction business later. If you want, though, you can just remember, think about it, flip a do, right? Do a little flip a do, cancel the 2's. Anyway, this one here, what's the integral of 5 cosine x? Well, the 5 is going to stay. So it's going to be minus 5. Integral of cosine, what equation gives me a cosine? The derivative of what gives me a cosine? Cosine, if I look at my rule, integral of cosine makes sine. So this is going to be minus 5 sine of x. So I change my cosine to a sine, right? Do the integral. Antiderivative. If you are ever confused, if you're not sure you did the antiderivative correct, think about it this way. Okay, if I had a sine, if I did the derivative of the sine, would I get a cosine? If I did the derivative of sine, would I get a cosine? Yeah, derivative of sine is cosine. We're okay. We're okay. So check it by going backwards. Check it in your head by doing the derivative. Especially for the trig ones. Especially for sine cosine, when you're like doing positive, negative, always check those. Last one here, plus 6. Adrian, what's this going to be? What's the integral of 6 going to be, Adrian? You should know now. All your fellow classmates helped you out. Did I lose Adrian again? Integral of 6, Adrian. Uh-oh. I think you started lunch early. I see. Not lunch exactly, so. All right, well, that's fine. Jessica, you tell me the answer here. What is the integral of 6 then? No worries. I'm sure it's fine. What's the integral of 6? Jessica, what's this going to be? Integral of 6. What do we do when we do an integral? What are we adding to the equation? Thank you, Kimberly. Stepping in. Pinch hitting. 6x. Yes, exactly. 6x. And then what do we need? What are we missing? We're doing something here? Plus c. I love how we work together in this class. So helpful. All right, let's simplify this. So we did all our integrals right. We got all our pieces right with the 6. We bring the 6 back in, right? We add our x's, add our x back in. So last thing, I'm going to do a little flip-a-do here with the 4/3. Just simplify this, clean this up. 3 times 2 is 6, divided by 4, though this 2 and the 4 are going to cancel. So it's really going to be 3x to the 4/3 over 2 minus 5 sine of x plus 6x plus c. And that's going to be our answer for this integral. So bring it all together, looking at these pieces here. Thinking about what equation would make that derivative, right? What equation would make that derivative? Okay, I'm going to do one more example. We got like 2 minutes left. I'm going to do a really, really tricky one. Tricky. And it uses the chain rule. Think of the chain rule. Think chain rule. What is the, what if I did the integral of 2x cosine cosine x squared dx? What would the integral of this be equal to? So let's think about what original equation, if I did the derivative of it, thinking about the chain rule, pardon me, what equation, if I did the chain rule derivative of that equation, would give me this piece here? Well, we know that cosine, right? What do we think? Think the chain rule here. Well, if I look at this x squared, there's kind of a clue here. If I look at this x squared and this 2x, I know that this 2x is the derivative of this x squared, right? And I know that if I have a cosine, my original equation had to be sine, because the derivative of sine is cosine. So if I think about, if I just had a sine of x squared plus c. If I had this equation here, if I did this derivative, I would do the derivative of the outside, right? This part is the outside, right? The outside. And this part here is the inside, right? Right, the derivative of the inside times the derivative of the outside. So we did the derivative of the outside part, which was to change the sine to a cosine, and then we did the derivative of the inside part, which gave us this 2x. There's like layers here. There's like layers sometimes. You can see the kind of chain rule pattern in certain derivatives. So that's going to be a couple questions that you're going to have on that. Here's what we're going to do. We're out of time, of course, but let me tell you what your homework is. Your homework is the handout on Schoology. So let me show you that handout, and then we'll be done.